Right, so let's get going then. It is 4:30. It's a pleasure to introduce our speaker today, Professor Alon Orlitsky. Alon has been a good friend of CLSP. He's given us good ideas on various things. He's come here once before, I think maybe 3 years ago, but he always has interesting things to say, so we decided to have him again. Those of you who need an introduction, he is the Qualcomm Chair of Information Theory and its Applications at the University of San Diego, University of California at San Diego. And he heads there an institute of some really famous information theorists called the Institute for Information Theory and its Applications. Just by way of biography, he got his bachelor's degree from Ben Gurion University in Beersheba in Israel. And then he came out, did a PhD, master's and PhD at Stanford, from where he went to Bell Labs, where he worked in the communications research division for a number of years. I would say he got his fame there. He got the Baker Prize. For those of you who don't know, this is a prize given by IEEE for the best paper in all its journals, transactions, proceedings, and so on once a year. Actually, they don't even give it every year now, right? They give it once in a while or something. And then he also got the IT Society Best Paper Award in '92, I think. And he's as famous as they get. And by the way, he has a very interesting sort of take on a lot of these estimation problems that we talk about. And he will tell you about that in a minute, and I'll not steal his thunder. I'll let him tell you what the main story is. Alon?
Thanks. Can people hear me like that? Is it okay? All right. Okay, so thanks a lot, Sanjeev, for the very kind introduction. Hope it didn't take you too long to memorize all these facts. All right, okay. So we are going to talk about 4 topics. And actually, let me start by introducing my co-authors here. Okay, so I'm going to talk about values and patterns, okay? Very hot topics sometimes, okay? And this is based on joint work with several of my former students, mostly with Prasad Santanam, Krishna Viswanathan, Junan Zhang, and also with Jayadev Acharya, Hirakenu Das, Anand Dulipala, Nikola Yevtich, Shengjun Pan, and Sajama. Okay? And we'll discuss 4 topics: compression, data compression, probability estimation, distribution modeling, and classification. And we're going to view all of them from a unified point of view, which we call patterns, which we'll describe. And because these problems are so basic, then a lot of famous people have looked at them, and we'll cover all of them, hopefully. And when I say hopefully, it's because there are 4 topics here, and realistically, this talk should take, and I'm going to give you a little bit of background to introduce these people, so realistically, this talk should take 2 hours, but we'll try to compress it a lot, so hopefully it'll be okay. And if not, we'll just stop wherever we get to. Okay. All right. Okay, so begin with compression, and start at the beginning, at least as far as information theory is concerned, 1948 with Claude Shannon. And he set up a very, very simple problem. He said, suppose you have an alphabet, which is just a set of possible outcomes, which we'll call A. So, for example, the binary alphabet 0, 1, or the English alphabet, a set of, let's say, words or set of letters. Okay? And what you observe is a sequence, which we'll call X over this alphabet. Okay, sequence of length n over this alphabet, and it's distributed according to a known probability distribution P. Okay, and I'm trying to decide which way I'm. Okay, and your goal is to convey X and to do it using the smallest number of bits. So what you do is you use an encoding, which we'll denote by Q. It's nothing but a function from sequences of length n over this alphabet to binary strings. Okay, and how do you measure the quality or the goodness of your encoding? You look at its the expected number of bits that it uses, okay? And we'll let that be L sub Q, the expected number of bits that Q uses. Okay? And natural question to ask is, we have many choices of Q. Let's choose the one that minimizes the expected number of bits, and let's call this L. That's the number of bits that you need, the expected number of bits you need to encode sequences of length n distributed according to P. And the question is, what is this minimum? Okay?
Given that Q must be invertible, right?
Yeah, so Q must be invertible. Q also must be prefix-free, but that will take us to 3 hours. So we're compressing, yeah, but it has to be number one invertible, and it has to be also prefix-free. Okay, right. And so the answer that I'm hoping everyone knows is that the number of bits you need is the entropy. Am I okay in assuming that the least expected number of bits you need is the entropy? And I wrote like this dot, small dot there, because it's not exactly the entropy. It's at least the entropy, and most the entropy plus 1. But for us, it's the entropy. Okay, all right. And furthermore, there's more good news. Not only can you find this answer it has a nice form, but also there are simple algorithms that achieve it, and that's like Huffman coding and Shannon coding. And one thing that you can observe is that in all those algorithms, the sequence X that you're encoding will get mapped into a binary string of what length? Log of 1 over p. Right? So if the probability is a half, this log is base 2, you'll map it into 1 bit. If the probability is a quarter, you map it into 2 bits. So this gives us a very strong analogy between compression and probability estimation. If you know the probability, then the number of bits you need is log of 1 over p. If you have a good compression algorithm, that means you also know the probability. Okay? Right, okay. And the light bulb there is actually for people who don't know, but I think people here know. So this is if we want an explanation, but I think even if people don't know, we don't have time for that. So, right, okay. So, but the question is whether there's a problem with this setup. There are problems, and one of them is that we made the assumption that P is known, the distribution is known, and in fact, except for homework problems, P is never known. If you're going to compress text, if you're going to compress video, nobody tells you what the distribution is, right? So you need to compress without knowing P, and then you cannot use log of 1 over P bits because you don't know what P is, okay? Right. So people observed it long ago, and the solution they came up with is called universal compression, and that's what we're going to describe next using basically the same layout. Okay, so depending on which hemisphere you live in, it would start by Fittingoff or by Davison, and again you have alphabet A as before, and you have sequences of length n over this alphabet. Except before you assume that the distribution was known in advance. Now you're going to assume that the distribution is unknown, except that it belongs to some known class P, capital P. Okay. Okay, so this class P could be the class of IID distributions or Markov distributions and so on. So what you'd say is, I'm flipping a coin, I know that it's IID, I just don't know the bias of the coin. Okay, I'm looking at text, I believe it's Markov, but I just don't know the transition, probabilities and so on. So, and you still want to compress the sequence, okay? So again, your encoding is going to map sequences of length n into binary strings, and LQ again is the expected number of bits that Q uses, except that beforehand you could get to the entropy. Now you don't know the distribution, so you cannot get the entropy, and you'll have to pay some penalty, which is the difference. So the number of bits that you use minus this entropy is going to be is a penalty that you pay for not knowing the distribution. Okay, and we're going to be very conservative, so we'll look at the worst penalty over all distributions in this class P. So we're using an encoder Q. It pays some penalty that depends on P. Okay, and we're looking at the worst penalty over all distributions in this class P, and we call this the redundancy of our encoding function of Q. Okay, and again we have a choice of Q to take, and we'll take the Q that minimizes this redundancy, this penalty. So we'll let R, the redundancy of this collection P, be the minimum of all Q of the redundancies. And the question is, what is this? What is the redundancy? Okay. All right. Okay. So again, and if this redundancy is a function of n, and it will grow with n, and so we normalize by n to see the per symbol redundancy, how much you pay per symbol that you encode. And if this ratio, if this normalized value goes to 0, that means that as the sequence length increases, you don't pay any penalty for not knowing the distribution in advance. So even though you don't know the distribution, you can compress to the entropy. And if that's the case, if the collection is such that the redundancy, normalized redundancy goes to 0, then you said that this collection P is universally compressible. Okay? And again, there is good news. And it says that all these collections, ID, Markov, stationary, ergodic, all these collections are universally compressible. So you can compress all of them without knowing the distribution in advance. And maybe the best known algorithm that achieves diminishing redundancy is the Lempel-Ziv algorithm. Okay, all right. And all these, I shouldn't say all, but many of these algorithms that achieve diminishing redundancy build on IID sequences. So you build an encoding that works for IID, and then you use it for Markov distribution, and so on. Okay. And so IID distributions have been studied very carefully, and people have shown that the redundancy of IID distributions is roughly half times the alphabet size times log n. So it's half the alphabet size minus 1 times log n. And you remember that we want to normalize by n, so you divide this by n. And you can see from here that there's good news, right? I mean, you see the good news here of universal compressibility, because as the sequence length goes to infinity, this behaves like log n over n. It will go to 0. Okay, so it shows you in particular that IID distributions are universally compressible. Okay, and so that's what we want. Okay, all right, log n over n. And is there a problem here, though? Okay, there is, and that is that except for homework problems, the alphabet size is never small, is never 2, right? If you're looking at, so the problem here is that as the alphabet size goes to infinity, so if now fix n and let the alphabet size go to infinity, the redundancy over n will go to what? Will go to infinity, right? And so this was observed by Kiefer roughly in 1978. Okay, all right. So in other words, and the point is that when you talk about compressing, let's say, speech, the alphabet size is not binary. The alphabet size is very large. If you talk about compressing images or compressing English text, the number of words is large. Okay, so what we information theorists we like you to believe is that the alphabet size is some fixed number, hopefully small, and the sequence length goes to infinity. But if, on the other hand, you say, okay, I have a given number, a given length, and the alphabet size goes to infinity, then the redundancy will go to infinity as well. Right? Okay. And in reality, of course, when you look at any real application, then the alphabet size might be the sequence length is some number, the alphabet size is some number, and typically the alphabet size is equal or maybe even larger than the sequence length. So there's someplace here, and we don't know. These results are only asymptotic. Okay. So is the issue clear? The problem clear? Okay. Right. Okay. So, So the solutions, there were several solutions people looked at, and so we'll mention some of them. Okay. So there were theoretical solutions, there were practical solutions, and on the theoretical side, people constrained the distribution. So instead of saying we're looking at all IID distributions or all Markov distributions, say we're looking at monotone distributions or distributions with bounded moments. So, but which would mean, like in monotone case, that the probability of a word that starts with A is higher than the probability of a word that starts with B. Okay? So clearly, this you can only assume if you're doing theory, right? Because in reality, that's not the case. Okay? So on the practical side, what people do is they don't want to deal with the high redundancy of large alphabets, so they convert sequences. Let's say they compress text. They convert words to letter or maybe even to bits, and then they compress those. Okay, so this is done in many implementations of Lempel-Ziv, context tree weightings, and so on. Okay, so the concern, of course, is that we may lose context, and the reason is that, for example, if you want to say that Bush was succeeded in 2009 by something, then we all can predict what the next word is going to be, or almost predict it. So we need a few bits to encode it on the average. Okay. But if you convert it to bits, it will be a long sequence of bits. And the way the systems work is they keep in memory what the context in memory, okay? And if you want to keep all contexts of size 270, you need a lot of bits. So you will not be able to keep that much memory. So maybe you'll keep the last 10 bits, which will be someplace here, and then you don't know what the next word will be, okay? So instead of these two solutions, we'll have a different solution, and that is we'll just change the question. Okay, make it a little easier for us, yes. Okay.
So if you're compressing to disk, you don't actually have to keep in memory the whole dictionary, because in principle, every time you wanted to look up something, you could go scan from the front of the file again, right?
Yeah, but the issue is...
It's certainly inefficient.
It's inefficient, number one, and number two, you convert it into bits, and the way it works is like you are trying to look at the context, and so you'll have this context appearing very few times, and you won't have enough statistics, so it's a problem that you'll have. Right. Okay, so we'll change the question, and so to see that, we'll see why you get infinite redundancy. Okay. So let's look at the simplest case where you get infinite redundancy, and that is, let's look at the alphabet. Well, we have to have infinite alphabet, so let's assume it's the natural numbers. And let's look at sequence length n. Let's say it's 100. It won't make a difference. Okay. So the collection P could be the collection, let's make it the collection P1, P2, where Pk is just outputs always K, the number K. Okay, so each Pk is a trivial distribution that outputs K, 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 K. So P7 will output 777 and so on. Okay. Now, if you knew K in advance, okay, we want to see what the redundancy of this collection is. So we need to compare the number of bits that you need when you know the distribution to the number of bits you need when you don't know the distribution. Okay. So if you know K in advance, how many bits do you need to encode 100 of those? Let's say you knew it was P7. How many bits do you need to encode 100 outputs of this sequence? Zero. Right? And that's because we know it's going to be 777, and this distribution is zero entropy. Okay? Right. Now, if we don't know K in advance, then we must describe K. And remember, we're very conservative, right? So we're looking at the number of bits that we describe for the worst distribution. Okay, and what is that going to be? Infinite, right? Because we're looking at the worst of all distributions in the collection. Okay? All right. So what we see is here the redundancy is infinity. And even if we normalize by n, it won't make a difference. And even if we let n to infinity, it will not make a difference because it will be infinite always. Okay? So, so this is really bad news. So what we see is that while if the alphabet is small, like binary, and you let the sequence length go to infinity, the news is really good. You can compress almost any collection universally. If your alphabet size goes to infinity, if you go up, then even for the simplest, most trivial distributions, your redundancy is infinite. Okay, so this is really bad news. But there's a silver lining, and that is that if we look at the number of bits that we used here, then all the bits describe the elements, and all the infinitely many bits describe the elements that appear, in this case 7. None describe the pattern, whether the sequence went up or down and so on. Okay? So the question is whether this is going to be the case always, okay, for more complicated collections. Okay? And we'll need to describe exactly what we mean by patterns. All right. So this is the hope, that we can convey all patterns efficiently. All right. Okay, so we described compression and saw how Shannon got in, and now we want to talk about patterns. Okay? All right. So what are patterns? So we want patterns to capture the structure of the sequence and ignore the symbols that appeared. Okay? Now, if you think about it for more than the 5 seconds that I'll give you, you'll see that there's only one way to do it, no more than one way. You have to do one thing, and that's what we're going to do now. You have to replace each symbol by its order of appearance. Okay? So let's see an example. So suppose you take this San Diego poem. It goes Sam-I-am and so on, and you want to look at a pattern. So the first word that appeared is Sam. Okay, so we'll call it number 1. The second word is I. We'll call it number 2. The third word is M. We'll call it number 3. Now, the next one is I, and I we've seen before, gave it 2, so it's 2 again. And then M, which again, we already gave it the number 3, so it's 3. And then same I, actually Sam is 1, and I is 2 again. And then do not like that. Those are all new words. Do, the last one was 3, so do will be 4, and then not will be 5, 6, and 7. Clear? And then semi-am we've seen here, which was 1, 2, and 3. So these will be, so semi-am will be 1, 2, and 3. Is that?
So I mean, the pattern here is the symbol for each word?
Yeah, so we are doing it per word. You could, if you want, you can do it per letter, or you can do it some other way. But
I just want to make sure that I understand.
yeah, so in general, you're given you have an alphabet, right? The alphabet A, which is known to you.
Because, for example, Samai could be a pattern too.
No, and yeah, so let's see what we assume is known. We assume that you know the alphabet, right? So you know the collection of possible elements. As you see here, it's a collection of words, okay, and each one is separated by a space, okay? If it was the collection of letters, you will have alphabet of size 26. And now you have elements from this alphabet, and each one, you give it the pattern the way we describe now. Okay, so is the pattern clear to everyone? What we mean by the pattern? Okay, so in that case, I have a small homework for you.
The message is that there are known knowns. There are things we know that we know. There are known unknowns. That is to say, there are things that we now know we don't know. But there are also unknown unknowns. There are things we do not know we don't know. And each year we discover a few more of those unknown unknowns.
So your homework, of course, is to find the pattern of the sequence. And just so you know, this pattern, dealing with patterns, is very rewarding, because this one got a prize. So, right. Okay, so everyone is okay with patterns, right? Right. So how would you compress with patterns? Okay, so let's say you want to compress this sequence. So what you do is you look at the pattern, and then you compress separately the pattern, namely 1, 2, 3, and so on, and the dictionary, which says that 1 corresponds to Sam, 2 corresponds to I, 3 to M, and so on. So in order to convey the sequence, you need to convey both the pattern and the dictionary, right? So you can talk, and when you think about it, it's kind of natural, right? Because you don't want to use the same compression, the same encoding for the sequence of words, because they satisfy a certain grammatical structure, as you do for the words which specify this, which look for the spelling of the word. You want to use different compression algorithms for both of those, so it's logical. It's also natural. If you're going to learn a new language, then the first word you'll hear, you'll call it number 1, then the second word 2. I mean, and then you say, oh, I heard this word again. They'll have no meaning for you. Okay? And so we're going to concentrate of these two things. We're going to concentrate on the pattern. The pattern dictionary will concentrate on the pattern, and for two reasons. One is because they capture the composition of the language and the structure, and its structure. That's one. And reason two, because they convey essentially all the information. So if you look at the entropy of the pattern in the dictionary, essentially all the entropy, a ratio that goes to 1, will be in the pattern. And this was shown by us and also Gemelos and Weissman in 2005. Okay? So we'll talk about the patterns. Okay, and I should say that related application of patterns was used for prediction by partial matching by Aberg, Starkov, and Smits in 1997, and Song and Shamir in 2004. Okay. Okay. So what is the question that we'll ask? So we'll look at IID distributions, because we know we need to start with those, over any alphabet, which could be large, infinite, even unknown. And we know that for sequences, Kiefer showed that the redundancy over n goes to infinity as the alphabet size goes to infinity. Okay? And the question is, if you do patterns, then we know that they convey essentially the same information as the sequence. And how does the redundancy over n behave there when the alphabet size goes to infinity? Okay? Right. Okay. So what is the plan? So we know that we saw that compression and probability estimation are about the same, because if you know the probability, then you know the length or that you're going to encode, and vice versa. So what we want to do is estimate the distribution of the sequences. And the slight difference is that now we're estimating distributions over large alphabets. So the point is this. If I flip a coin 100 times and I see 60 heads and 40 tails, then I know the probability of heads is 60%, right? It's not very difficult. But what happens if I do an experiment 100 times? Instead of seeing just 2 values, heads and tails, I see maybe 80 values. So most things will appear at once. So then how do you estimate their probability? And then you know there are things that you have not seen. How do you estimate their probability? Okay? So that's the question there. And we'll talk about existing estimators, and we'll talk about empirical frequency, which we'll show performs poorly. We'll talk about Laplace estimator, which is better but not good, and good Turing, which we'll show is good but not optimal. And then we'll talk about a new estimator that is based on work by Hardy and Ramanujan and is, in some sense, asymptotically optimal. Okay. All right. So we talked about now patterns, okay, and we want to look at probability estimation. All right. Okay. So imagine that you are preparing for a trip over the summer, and you want to estimate the distribution of different animals that you're going to encounter. Okay. So what you do is you may go on the internet, and you observe a sample of animals, and maybe this is what you see. So you see one giraffe, two elephants, and three zebras. Okay, and then from that you want to say, okay, here's the distribution of animals that I'm going to see. Right? So what would that be? Okay, so the simplest estimate would be empirical frequency, that we say, okay, so the total of 6 animals that I saw, of them 1 was giraffe, so giraffes are probably 1/6, elephants are probably 2/6, and zebras 3/6. Right? It's reasonable. Is there a problem here? Or a line. Okay, so there are things that, they might, be dangerous for you if you do this assumption. Okay, and this was an observation that bothered actually the French a long time ago, about 1800, and they noticed that the sun rose and rose and rose and rose, and they said, what is the probability that the sun will rise the next day? Okay, and so they saw it rose, but then still there could be a different outcome someday, and so they have different ways of estimating the probabilities of, like, maybe, like a bank, like the financial system going, bankrupt and so on. And the method that remains to this day was devised by Laplace. Okay, so he of course is known for a lot of different things. Okay, and so he was. Well, there are many things he was, in fact, that he did, and he was so well known that actually Napoleon made him the Minister of the Interior. But so he's probably like the most politically advanced of mathematicians. But he didn't last in this position for too long, because Napoleon fired him about a month after he appointed him. And when Napoleon himself was fired, he had some time to reflect, and he wrote that Laplace brought the spirit of the infinitesimally small to the management of national affairs. So I'll explain why. But at least for this respect, he did a better job. Okay, so what was his estimator? He said that you add 1 to any possible category, including to new. So the sun rose. Look at the age of the universe. You add that to 1 to that, and then the sun rose all of those times, and then it didn't rise 0 times, so you add 1 to that. So the probability the sun won't rise is 1 divided by the age of the universe plus 1, and then plus this 1. Okay? So is this clear? Okay, if not, then hopefully it will be clear in a second. So if we look at our example, then giraffes, we saw 1, we add to them 1, so you get 2. And elephants, so 2, you add 1, you get 3. Zebras, you get 4. And then so 0 times, you get 1, you add 1. Okay, so your new estimate, when you total these new numbers, now you get 10, because it was 6 before, and then you added 4 once, 10, and now giraffes, you get 2/10, 3/10, 4/10, and 1/10. Is this clear? Okay. Now, clearly, you can come up with many at constant variations. Okay, and you don't have to add 1, and indeed, people add other things. Okay, but the question you can ask is whether these estimators are good. Okay, so it turns out that in cases like this, when your alphabet is small and your sample size is large, they are very good, actually. Okay? But our question is, what happens when the alphabet is larger? Okay? So to see that, imagine DNA sequences. So let's say that we're trying to find the distribution of DNA sequences, okay, which is a very, very silly question to ask, because we know there's no distribution. Every person has a unique DNA sequence. It's not that one DNA sequence is common to 10% of the population, another DNA sequence common to 5%. Everyone has a unique DNA sequence, but that's what we want to find out from the data. Okay, so what we do is we take the DNA of n people, and n is large, okay, and sure enough we find that they're all different. And so let's see what the Laplace estimator would do. So each observed sequence we'll see once, we'll give it a count of 2. Okay? New will give it a count of 1. Okay, so what is the distribution? So every observed sequence, so the total, you have these 2 appearing n times, so these give you 2n and n plus 1, so this is our denominator that we just need to normalize so that the values sum to 1. Each observed sequence we give probability 2 over 2n plus 1, and nu we give 1 over 2n plus 1, right? Is there a problem with that?
Identical twins.
Right. So even they may not share, right? I mean, I'm not sure. But is there other problems?
It sounds wrong.
Yeah, it sounds wrong. Yeah, I agree with you. That's like the main problem. And that is, if after we do this, after we do it to the whole universe, and we ask what is the probability of nu, that the next person will be nu, then according to this will be different from what you've seen. According to this, we give it probability which is 1 over 2n plus 1, or roughly 0. But we know it actually should be 1.
No evolution.
No evolution, right? No mutations. So we know it should be 1, and whereas Laplace would give it probably which is close to 0. So it doesn't learn that everything is new, that everything is different. And the probability that Laplace gives observed is going to be 2 over 2n plus 1 times n for all the observed one, which is roughly 1. Again, it's the complement. So the opposite is more accurate. Okay, all right. So, okay. So this was the problem that good Turing have encountered. They surely knew about this, and let's just give the background of why they came across it. So this is roughly early 40s, World War II, and this is Germany, and these are the Allied forces, and you can see there's very little red and a lot of blue, and some people in England and the US were somewhat concerned. And so they had convoys that were trying to supply Britain with both military and civilian supplies, which were essential to them at that time. Okay, and what ensued was the battle. So this is the first time I'm showing the slides with this thing, so I guess it doesn't show very well. Okay, it was the Battle of the Atlantic, in which 175 warships, Allied warships, were sunk, and over 3,500 merchant vessels were sunk. So if you figure that this is roughly 4 years, so that's roughly 900 per year. That's roughly somewhere between 2 and 3 ships every day that were sunk, okay, and 30,000 sailors. Okay, so, and the main culprit in this were the U-boats. And so U-boats, can you see? Okay, all right, something to know. Okay, so U-boats should say someplace there. It's like the English nickname for the Unterseeboot, which is undersea boat. And the Germans built about 1,000 of them, okay? Each of them with roughly 15 torpedoes. And Churchill, in fact, said that the only thing that really frightened him during World War II was the U-boat Pearl. Okay? So one of the reasons they were so effective is because of this device. It's the Enigma machine, which was invented during actually World War I, but was improved between World War I and II. And basically what it is you see here the rotors. Each rotor performs a permutation code. So it takes A, maps it to like K, and every word to some other letter. And then, you repeat it, in this case 3 times, but as time went by, they went up to 6 rotors. And what happens is that every letter that you type, each rotor moves, and so the permutation changes. And then when this rotor completes a circle, then this one will move. So every time you're using a different permutation. Okay, so it's quite difficult to break. Okay, and in order to break this, the British had a major effort in Bletchley Park. This is about 50 miles northeast of London, and in this effort, they managed to break the Enigma and the Lorentz ciphers, and as a result, they sank 783 U-boats. Actually, I shouldn't say as a result, because this is only part of a very big effort. Okay, and there are some estimates that this effort shortened the Bletchley Park effort shortened the war by 2 years, and Churchill had the following to say about them. So, anyways, okay, so part of this effort, they actually built the first computer. It was called Colossus, built in 1943, but even though they had a computer, clearly it was not as powerful as what we have on, I don't know, on my cell phone. And so they also had about 10,000 people working there. And some things that they did was they were trying to look at statistical clues and follow them to break the ciphers. And there are a couple of things that helped them. And that is that they captured a German U-boat, and therefore they captured, one, the Enigma machine, and two, that the Germans did not trust the U-boat commanders to choose the passwords, because they knew, even then, before computers, they knew they were going to choose, the wife's name or the girlfriend's name or interchange them. So they gave them a book of keys, and they had to choose a key from that and change it every single day. Okay, so here's a page from the book of keys, and as you can see, there are lots of pages. Clearly, lots of pages, a lot of lines, a lot of columns in this page. Okay, and so what they were trying to do is they were trying to improve their guesses. So based on past choices of the passwords, they tried to see whether each commander is going to choose which page each commander is going to choose the word from, is more likely to choose from the beginning of the book, from the end of the book, from the top of the page, from the bottom of the page, and so on. So you can see that there are many possibilities and few decryptions. So it's very similar to what the problem we're interested in, which is you have a large alphabet and few samples. Okay. All right. So this is where Good and Turing come in. And Good in Turing, he graduated from Cambridge in 1934, so a few years before the war, undergraduate degree. And just interestingly, this is, mind you, before computers. As we said, the first computer in 1943. He talked about he did his research on computability on Turing machines, invented in this paper, in fact, computable numbers. Okay, and also talked about the halting problems and undecidability, all this before computers even existed. Then he went to the Institute of Advanced Studies and got his PhD in 1938, and then joined Bletchley Park. So he was a very natural person to work on these things. Okay, and I.J. Good, he born a little later, and he actually just finished his PhD under G.H. Hardy just before the work started, and then he went to work at Bletchley Park as a statistician, and became very famous afterwards, I should say. Okay, so let's see what the estimator was. Okay, so for Laplace estimator, we needed one picture from the internet. For the Good Turing estimator, we need the Noah's Ark. Okay, so here it is. So let's say that we have one giraffe and one rhino, 2 elephants, 2 lions, 2 cheetahs, and so on, 3 zebras, and so on. So empirical frequency will give each animal a probability which is proportional to the number of times it was seen. Okay? So giraffes will give probability which is proportional to 1, elephants probability which is proportional to 2, and we need to normalize. There are 19 animals here, and need to normalize by 19. Laplace will give a probability which is proportional to the number of times it was seen plus 1. So instead of 1, it will be proportional to 2, instead of 3, proportional to 3, and then you normalize by 29 to make a probability distribution. Okay? Now, let's look at Good Turing. So, Good Turing will start with the Laplace estimator. This is one way to describe the Good Turing estimator. It's not the only way. We'll start with the Laplace estimator 2 and 3, and then we'll trick it. How will we trick it? We'll multiply it by the number of animals that appeared once more than the animal we're considering, and divide by the number of animals that appear the same number of times. Okay, so let's look here. So there are 2, in this case, there are 2 animals that appeared once. There are 4 animals that appeared twice, and there are 3 animals that appeared 3 times, okay? So when we look at giraffes, we'll take the 2 that we had before, and we'll multiply it by 4 and divide by 2, okay? And we get 4. When we look at elephants, so they appear twice, and we multiply by 3 and divide by 4, okay? And get this, okay? And then you need a normalization factor, which is 19, okay? Is that clear? Is there a problem? Right. What happens to zebras? Zebras, we should get the highest probability. But if we multiply by the number of animals that appear 4 times, we'll multiply by 0. Okay? So we'll get 0. So the animals that appeared the most times will get the least probability, 0. Okay? But that is a problem for people like us, not a problem for good in Turing. Okay, they could see beyond that. And so they saw that it requires a little bit of smoothing and so on, but there are many techniques that you can use to smooth them, and you get a family of estimators, and some people say you get a religion of estimators, okay, depending on what kind of smoothing you do. Okay, so some observations. So it's surprising. Surprising because why would you look at how many animals appeared more than you did? Why would you care about that? Okay? And could be complex depending on the smoothing that you do. Okay? But it works well for infrequent elements, okay, for things that appeared a few times. So it's used in speech recognition, machine translation, data mining, all the stuff that you know a lot more about than I do. Okay? And yet it's clearly suboptimal for frequent elements, because if one animal appeared like half the time, then clearly you are going to no animal appeared half plus 1 in that case, so you'll give it 0 probability. So it's suboptimal for frequent elements. So what people often do is they use empirical frequency for frequent elements and good Turing for infrequent elements, and there are many ways of combining these two and so on. And there were several motivations that were described for good Turing. Okay, so the first one was by Good himself, who published the paper about this method in 1953. And in this paper, by the way, he writes that Alan Turing deserves a lot of credit for this, because he gave him the formula along with an intuitive explanation. But he doesn't quite say what Turing's intuitive explanation is. Although he does give an explanation, we don't know if it's the same. So that's one motivation or explanation. And then there's another one by Robbins, and then there's another very nice one by Jelinek and Professor Jelinek and Mercer in 1984. So these explain why you might want to multiply by the number of elements that appeared more than you and divide. But they don't give rigorous results that say, okay, if you do that, then this is optimal. They just say, okay, this is a reason to do it, and it's natural to do it, but there's no like proofs that if you do it, it's optimal and so on. Okay? So in terms of formal evaluations, then there was McAllister and Shapiro in 2000 came up with one, and then we had one in 2003, and there are some others after that. Okay. All right. So what is our further plan? Okay, so we want to define a measure for evaluating estimators, which we call attenuation. And we want to evaluate empirical frequency, Laplace, and good Turing. And I'll have to skip a lot of that because of timing. So, and then say how Hardin and Ramanujan come into the picture, okay? And then describe the optimal estimator. So let me say what the attenuation measure is. So we assume that there is an underlying distribution P, which is unknown, except that it belongs to some class P, okay? And in this, we're going to assume that P is the IID distributions here. Can we observe a sequence X? And we're going to assign it some probability Q. Q is our estimator, Q of X, okay? And we want to compare Q, our estimator, to P, which is the real one. But the problem is that the real one is not known to us, so how can we compare? So what we'll say is that we want Q to be almost as high as this P that we don't know, okay? Now you can ask, why do we want to be almost as high? Why are we worried about underestimating and not worried about overestimating, okay? So we'll come back to that. Okay, so formally here's the definition. So we look at the ratio between P and Q. P, mind you, we don't know, but it's there, it's some number. We look at the ratio between P and Q, and we're being super conservative. We're going to maximize this ratio. This is our attenuation, how much we are below P. We're going to maximize it over all distributions in the collection and over all sequences. So we're being very, very conservative, okay? And this is for a sequence of length n. We want to do it per symbol, so we take the nth root and we let n go to infinity. So I want to see what happens when n goes to infinity, okay? So this is the asymptotic per symbol worst case attenuation, okay? And this is the largest underestimation factor per symbol. Okay? All right. So some observations. So in the worst case, we underestimate each symbol by this factor because this is our definition. Okay, so we want low attenuation, okay? And since both P and Q are probability distributions, right? P is some distribution that we don't know, and Q is what we come up with, which is a probability distribution. So this is P, and here is our Q. And so they both integrate to 1. So there must be some location where our Q is less than P, right? Like in this region. Okay, so therefore the attenuation, we must attenuate someplace. And we're looking at the worst case, we must have attenuation, which is at least 1. If the attenuation is strictly bigger than 1, that means that we underestimate each symbol by a factor of this attenuation, which is bigger than 1. And therefore, we underestimate the whole sequence exponentially by this factor bigger than 1 raised to the n. If the attenuation is 1, that means that we underestimate this symbol by a factor that goes to 1, and we underestimate the whole sequence sub-exponentially. Okay, so that's our goal. Okay. And okay, so now motivation. Why do we care about attenuation, about underestimation? So first of all, if the attenuation is 1, that means that we do not underestimate. Okay, and at least for 2 people, or it's important not to underestimate. Okay. Now, also, if you don't underestimate, then it also means you don't overestimate in some sense, right? Because P and Q integrate to 1, so if you overestimated, like here, if Q was bigger, then there must be another place where Q is smaller. And if this does not exist, if Q does not underestimate, you also cannot overestimate. Now, this is not exact, because maybe over a whole region you underestimate by a little bit, and then over one location you overestimate by a lot. It's possible. So that's why this line is a little crooked. But in some sense, it's correct. Okay? And then you can show that if your attenuation is 1, then the KL divergence is going to go to 0, because the KL divergence is just the expected ratio of the log of P over Q. And P over Q now going to go to 1. Log of that will going to go to 0. Okay? And so it will give you this, and then you can show that in that case also give you diminishing variational distance. So the L1 distance is also going to go to 0. So attenuation is stronger than it appears, and it's simple to define. And furthermore, maybe equally importantly, you can show that the attenuation can be made to be 1. Right. Okay. So let me skip a few slides here. So this slide just shows you that the attenuation of empirical frequency is very high, and the attenuation of Laplace, namely infinity, is also infinite. Okay, so Laplace attenuation is also infinite. Now, good Turing, like we said, there are many versions, and we looked at 3, and of them actually we can analytically analyze only 1, but we can evaluate 3 experimentally, the other 2 experimentally. And for simple good Turing, which is possibly the simplest one you can do, you can show that the attenuation is at most 2. So no longer is it infinite, it's at most 2, which is good. So you underestimate each symbol by a factor of at most 2. But on the other hand, it's at least 1.39, so that means that you underestimate the whole sequence, but 1.39 raised to the power n, which you may not like. Okay, and then Church-Gale, this you can do analytically. Church and Gale, at least 1.2, and common sense, which is the empirical frequency for common elements, and good Turing for infrequent elements, exists at least 1.5. These 2 are experimentally. Okay. So the problem in all of those is you get potentially exponential sequence attenuation. Okay. So diminishing attenuation using results by Hardy and Ramanujan, you can build an estimator whose attenuation is at most 2 to the square root of n for the whole sequence. So when you take the nth root of that, it will be like 2 to the 1 over square root of n, which will go to 1. So, and then you can also, with a slightly slower convergence, you can do it sequentially and with constant number of operations per symbol. Okay. So let me skip the connection also to Good and Turing, just because I'm sorry, to Hardy and Ramanujan. The connection is via the partition number, which is the number of ways you can write a number as a sum of integers. So for example, 4, you can write as 4 or 3 plus 1 or 2 plus 2. You can write it in 5 different ways. Okay, and what Hardy and Ramanujan showed, so we're skipping the story, is that the partition number is 2 to the square root of n. So it's sub-exponential, which is what we need. Okay, so you can show that the number of different parameters that you need to learn when you look at the patterns, the probability of a pattern. The number of different parameters that will give you the probability of the pattern is the partition number, and therefore it's 2 to the square root of n. So you have at most 2 to the square root of n parameters that you need to describe, and because of that, your attenuation is at most 1 over 2 to the square root of n. So I don't have time to get into that, unfortunately. Okay. And so this is the connection between the 2. So I had some, I should say that I had some hallucinations of going over time in this talk, but then I was told that Professor Jelinek used to come here with a huge clock to come, not here I assume, but to this, the predecessor of this seminar with a huge clock, and when the time came, he would just wave it to the speaker. So right, so just want to avoid the situation. So I'm just skimming through things just to get to more topics. Okay, so this is
Somebody stole the clock.
Oh, in that case, let me go back. All right. Okay, so you can get also a lower bound. You can show that the attenuation, we showed that we have an algorithm that gets you attenuation of 2 to the square root of n. You can get an attenuation, the best you might be able to get is 2 to the cube root of n, but the gap is an open problem. Okay, all right. So let's do a small test and then briefly talk about one of the other 2 topics. Let's skip the test. You're all very smart. We know that. That's right. Okay. So this test was supposed to see, like, if I give you a sequence, how you estimate the probability of the next symbol. Okay. But I'm giving you all the answers, and you can figure them out later on. Okay. So once we have a way to estimate probabilities with low attenuation, you can use it back for compression. So if you remember, for compression, we were worried about what happens when the alphabet size goes to infinity. But now we have a way to estimate probabilities such that we underestimate by at most a factor of 2 to the square root of n. That means that the probability that we give to each sequence is at least its probability divided by 2 to the square root of n. And so 1 over our estimate is at most 2 to the square root of n, the reciprocal. 1 over 2 is at most 2 to the square root of n, bigger than 1 over p. And if you remember, the number of bits we assign is log of 1 over q, which is our estimate. So this is going to be at most log of 1 over p plus square root of n. So what we see is the redundancy, the extra number of bits that we pay is at most square root of n for the whole block. And that's independent of the alphabet size. It's true for any alphabet size. Okay? And when you divide by n, it will go to 0. Okay? So, and this can be done so this shows that patterns are universally compressible, sequential, and can be done sequentially and efficiently. And so instead of the question, we have the answer that if you have patterns, then the normalized redundancy goes to 0. And the picture, instead of like that, it goes like this, so that for if it goes down uniformly in n. So if you go far enough for n, the redundancy is at most square root of n, regardless of the alphabet size. So if you go to length 100, your redundancy is at most 1 over 10, no matter what the alphabet size is. Okay. If you go to length 1,000, your redundancy is at most 1 over 33, regardless of the alphabet size. Okay, and this can be done efficiently. Okay. All right, so distribution modeling, let me go very quickly over that. So in distribution modeling, what we talked about until now is probability estimation, where you try to estimate the probability of things that you have seen and of new things that you have not seen. Okay, so for example, if you want to say the probability of heads is 0.3, the probability of tails is 0.5, then probability of new is going to be 0.2. We want to talk about distribution modeling, where what you care about is just the probability of the elements, including unseen, but on the other hand, you don't want to associate the probability with the elements. So in this case, you'll just say the probabilities are 0.5, 0.3, right? 0.5, 0.3, and 0.1, maybe these are the things you have not seen. But you don't say which one is 0.5, which one is 0.3, and so on. Just to have the set of, or the multiset of possible probabilities. Okay? Now, why would you care about this? About just the multiset without the association? Well, maybe you care about the support size, like how many elements are in your distributions, or maybe there are many applications where you just care, like you're building a wireless network, and you want to know what is the probability that the demand will exceed the supply. So you want to know what is the probability that each person will want to communicate at any given time. You don't care what is the probability that I will want to communicate, just about the set of probabilities that are there. So there are many cases where you just care about the probabilities, no association with the people. Okay, so we're skipping all of those. Okay, so so this, again, there's a nice story about this, about trying to estimate the number of butterflies in what's now Malaysia, and there's a long history to that as well. So I just want to show you maybe a couple of experiments. So, okay. Okay, so the approach that we take, so one simple approach is to do maximum likelihood. So if you flip a set of coins and you get, let's say, heads, heads, tails, then you might say the probability is 2/3, 1/3. That's the normal thing to do, okay? And that works well, that's reasonable, okay? But what if you take the DNA sequence and you see 100 different elements? Then if you do maximum likelihood will always give you the fraction that things appeared. So we'll tell you that you have 100 elements, each with probability 100, 1/100. That clearly is not a very poor estimator. A much better estimator would say it comes from a very large alphabet, right? Because you do DNA sequences, so each one appearing once, so you say it must come from a larger alphabet, but empirical frequency does not say that. So one thing to observe is this, that the actual elements don't matter. The only thing that matters here is the pattern. The only thing that matters when you try to, if you try to estimate, you're not trying to associate probabilities with elements. You're just trying to come up with a set of probabilities. So the only thing that matters is the pattern that you saw, okay? So instead of doing sequence maximum likelihood, why not do pattern maximum likelihood? So if you look at the DNA sequences like 1 to 3 up to 100, then the pattern is 1 to 3 up to 100. And when you ask yourself which distribution will maximize this pattern probability, that's a distribution over infinite support. Because this just says that every element appeared once. If your support is infinite, that will give it probability 1. So that's, you see right there that it gives you, for this case, a better answer. And you can do it also for the coins, and you'll see that will give you half-half. And actually, when you think about it, it will make more sense. So let's do show some experimental results. Okay. So here we took a distribution, uniform distribution over 500 symbols. Yes.
So
go ahead.
I'm confused about the infinite support conclusion.
Yeah. Go ahead.
So I don't understand how you would have that distribution. What is that distribution with infinite support? So it's got to sum to 1 over infinitely many things.
Right.
So if it gives each of them positive probability, then there's a positive chance that you don't, in fact, have probability 1 of getting this sequence.
Right. So
maybe it still maximizes the
right.
probability.
It's a very good question. Yeah. So I'll give you 2 answers, which I don't have one good one. But so you can define this as the supremum of all probabilities. Okay. So if you take a uniform distribution over n elements, then you can find the probability that you'll have a repeat, which will be, if it's uniform, will be exactly 1 over n. The probability that the second one is equal to, right?
And the probability of this one increases and goes up.
Right. So you can take the limit, and so as you get closer to an infinite support, you'll get the distribution goes to 1, right? But we don't like this because we want to be able to find the highest distribution. So the way we get around this, which I think is an okay way to do it, is we said that your distribution consists of discrete elements, like in this case that you're concerned with, and also a continuous part. So you have a discrete part and a continuous part. So maybe sometimes you're going to go into, like, either you take like one of those elements or you pick something from a continuous part, and then you do that. So in this case, the maximized distribution will be continuous over an interval. So then you can always achieve it. The supremum is always achieved. You can show. Okay. Right. So, but in any case, even if you don't like this infinite support, you see that it will tell you intuitively. It definitely tells you that it comes from a larger support, right? I mean,
so it's fine if it's uncountable.
Yeah, because again, so right now we describe what the distribution comes from, right?
Just to be clear, when you say the patterns, let's take the coins case, the 1, 1, 2 case, right?
Right.
So you want to find the distribution under which the likelihood of the sequence heads, heads, tail, and the sequence tail, tail, heads, the union of those two is maximized.
That's exactly right. So we're looking. So this pattern, when we got heads, heads, tail, the pattern is 1, 1, 2. But this pattern could be derived also from tails, tails, heads. And so the union in this case is going to be p squared q plus q squared p. Okay, and then you want to maximize this over P and Q. Furthermore, you also want to maximize it over PQ and R because you don't know over PQRS and PQRS and the continuous part. So you're looking over all possible sets. And in this case, it's still distribution over 2 elements. Right. Okay. All right. So experiments. So uniform distribution of 500 symbols is shown here in red. And then we took 250 samples. So in this run, you got 6 elements appearing 3 times, 45 elements appearing twice, and 142 elements appearing once. and 307 elements. Because see, if you have 250 samples, the most you can see is 250 of the 500. In this case, you saw 193, and 307 you did not see at all. Okay? So this is what you saw. And if you did the empirical frequency, it will correspond to just or maximum likelihood to what you see. Okay, and this is what you have here. Now, if on the other hand you ask what will maximize the probability of the pattern that you saw, just maximum likelihood on the pattern, you'll get this blue line. So number one, it figures out that there are about 500 elements, and number two, it figures out that they are almost uniform. Okay? If instead of instead of 250 samples, you go to 1,500 samples, then again the same distribution. Then now every element will be sampled roughly 3 times, and indeed it figures out that there are roughly 500 elements, but the distribution is not uniform. And yet, if you try to maximize the probability of this pattern that you see, then you get something which is almost essentially right. Okay? And then you can repeat it. Of course, we're not making the assumption it's uniform, so you can repeat it for other distributions. It's looking at the distribution of Shakespeare's vocabulary is fairly popular. So here is an experiment that we did. So this is the actual distribution. Okay, so he wrote about 900,000 words, of which about 28,000 are distinct. So this is this distribution of the distinct word. This corresponds to once. You see a lot of them appeared once, like 12,000 appeared once, like this. Okay, and so what we did was we sampled 90,000 out of this, about 10%. And this is what you get by empirical frequency or maximum likelihood, and this is what you get using our method. So it doesn't get everything, but you realize that here you have things that appeared once. I mean, and we don't know what it is. So, okay. And then there is another experiment with last names, people's last names. Okay. So this is the distribution modeling, and finally classification. Give me 1 minute, maybe. So the idea is that, so we believe we have a decent way of estimating distributions, right? So we say, why not apply it to estimating distributions of words and then use it to classify documents, okay? So here you look at, you have documents that are pre-classified into topics, and topics could be business, technologies, politics, and sport. And what we want to do is test, a new document comes, we train on the set, and we want to find a topic. And there are many existing methods. Probably the state of the art might be support vector machines. And what we would do is just take the basic approach, which is just estimate the probability, okay? And but just use our equivalent of the good Turing estimator to do it. Okay, so we model words as IID. We train separately for each topic and use the probability estimator that we have. We have several, but we can only use the efficient one. I didn't talk about this, but the one that achieves square root of n to n square root of n is inefficient. We have another one that is more efficient. Okay. So we estimate the probability of each word and of new ones. Okay, and then given a classified document, determine the probability of each topic. So for each topic, we have a distribution and then determine the document probability and use naive Bayes. Okay. All right. So so this is a result for news groups. We won't go over them. Let me just show you the summary. So we tested on 3 data sets. One is Reuters news groups and CADE, which is a Portuguese database. And then we checked Laplace support vectors machine and this approach. And you can see that the Laplace does fairly poorly, but not much, but does worse. And these 2 techniques, I would say, are comparable. Maybe they're a little better than us in one case, or a little better than they are in 2 cases. But in any case, I would say they're comparable. And support vector machines are very complicated. There are lots of things you need to tweak. And here you just apply this probability distribution, and you get essentially the same answer. Okay. So conclusions, I'm hoping that I showed you that information theory has some applications. And when you learn only from data, then maybe what you want to do is call the first element you see 1, the second element you see 2, and so on, and then analyze this pattern the statistics of this pattern, and then the calculation will differ from the sequence elements, and for small alphabet size, you'll get the same values. For large alphabet size, you get the results that are different, and it works reasonably well for compression, probability estimation, distribution modeling, and classification. Okay, so thanks. Yes.
So far, whatever you say, it's all discrete alphabet.
Correct.
Do the same conclusions hold in continuous case, or?
No, that's a very, very good observation. So everything we said before applies for discrete alphabets, and that's a very big drawback of this thing. We have been working, and we are working on extending it, trying to extend it to continuous alphabets. Definitely, the same results will not hold. We have some results, like about some special cases of continuous alphabets where you can say something, and we've presented some of those. But yeah, clearly they're not as good as these results, and that's a very interesting topic. Yeah. It's probably the biggest drawback of this.
I have a question about the pattern. So one of the things that happens is that if you assume things are coming from some sort of IID family, then the counts of various symbols tend to be the sufficient statistics, right? And so when I say the sufficient statistics, what it means is the sequence that I observed, any permutation of that sequence also has the same type class. And so when you do maximum likelihood estimation, you're trying to maximize the probability of that set of samples. Meaning you observe one of them, but you treat them all as equivalent.
Correct.
So when you do patterns, you're creating a new set of equivalence classes, right? A new equivalence classification.
Right.
So how do the two compare, and is there a connection between them? Because clearly a pattern has a similar flavor in the sense that if the thing seen once was seen 3 more times later,
Right. then
there is that connection. But I'm trying to figure out maybe you can say a few words about it.
Right, yeah. So that's another very good question. Sanjeev's question is as follows. Suppose I'm looking at a sequence, I get heads, tails, heads, okay? And I know it's IID, like here we're assuming it's IID. Then I may as well just say I got 2 heads and 1 tail. I mean, we might look at specifically I got that sequence, heads, tails, heads. We can just say I got 2 heads and 1 tail. What is the distribution, okay? And here, so this is one way of looking at sufficient statistic. And we're looking at a different one. We're saying we're not going to call heads heads. We're going to call the heads 1 and tails 2. And
whichever appears
first one, that's right, and second 2. So we're again combining them. He's asking, is there a connection? So there is a connection. Furthermore, I would say what you could do is you could do the same thing for the patterns as well. And in fact, if we look at here, because even the pattern has the sequence information, but you can say that, like if I get 1 to 1, that's the same as 1, 1, 2. I mean, that has the same probability. So you can do that too. And here there's an even further one, the further generalization, that 1, 1, 2 is the same as 1, 2, 2. So what you care about is how many elements appeared how many times. And so what in the sequence case is called a type. I've seen 3 heads and 4 tails. Here we call it the profile. The profile that you have. I've seen so many elements appear twice and so many elements appeared once. And in fact, you can do all the calculations and you do on this profile. So when I showed you this I didn't want to introduce new terminology in negative time. But when I showed you this experiment, I told you that we have seen 6 elements appear 3 times, 45 elements appear twice, and so on. So this is the equivalent of the type. This is the profile. So actually, it's the profile that we try to maximize. So you can combine these two.
Right. So this is sort of an even larger
Correct.
set of sequences
Correct.
than the type class. So
Correct.
if there is one type class with 3 heads and 2 tails,
Right,
another
they're
one
combined with 2 heads,
3
exactly.
tails, but they have the same.
Yeah, and in general, so you'll say how many elements appeared how many times. So in this case, you'll have 1 element appeared 3 times, and the other elements appeared 4 times. That's if you have heads and tails. But now if you have multiple values that could appear, you say so many elements appeared 3 times, here's 6. So many elements appeared twice. So many elements appeared 1. That's exactly what we do. Sorry.
So a natural question to ask about this method is whether it's divisible in the following sense. This is, I'm sure, something you've looked at. I don't know if I'm right in calling it divisible. I think the answer for Laplace would be no, but I'm hoping for you it might be yes. So suppose I have my secret alphabet and distribution, and I generate some data from that, and you estimate. And then I tell you, actually, the words were in equivalence classes. So I'm really only interested in the probabilities that you assign to my equivalence classes. So I'm going to tell you the equivalence classes. Okay?
Yeah.
Okay?
Right.
Now, so you've estimated a distribution based on the fine-grained data, and then you've coarsened that estimate to only assign probability to the equivalence classes. Now, do you get the same answer as if I had only shown you a coarsening of the sequence and you'd estimated directly from that?
Yeah, so I don't know that I'm afraid that the strict answer is no, because we have combined, when we look at 1, 2, we've symmetrized all the elements. So 1, A and B were the same for us, right? So I don't know that if you're now going to combine specifically A and B, then we can reduce it from the data. So the way I would...
Well, I'm not asking you to recover it. What I'm saying is, at the end of the day, you say, okay, you have a distribution over 10 things, and their probabilities are this vector that sums up to 1.
Right.
This vector of length 10 that sums
That's
up to 1.
right.
Now, if I pair them up, before I generate, you're going to have a vector of 5 things, and my question is whether that vector of 5 things that you estimate.
I'm guessing the answer will be different. So if we were going to do your question, we can do it in 2 ways. One is what you've said. So look at the data, and then whenever if A and B for you are the same, then whenever you see A and B, you call it 1, and then use it as one class. Or after you've done this training, then you get a distribution. Let's say you've seen the symbols 1 up to 10. They appeared 1, 1, 2, 3, 1 again, and up to 10. 10 symbols altogether. Now, after you do that, what you'll get is you get a probability for 1. You get a probability. We'll give you a probability for 1, probability for 2, probability for 3. But you will know which is 1. Because you've seen the first element is you know which one it is. A is 1, and B or C is the second one that appeared. So then if you want to look at the probability of A and B, then you can just look at the probability that we gave to 1 and 3, if those were the corresponding and add them. I suspect that the 2 answers will be different.
Actually, I already have a counterexample based on your all distinct elements case.
Yeah.
Yeah, so they may not come out the same.
Right, yeah.
So that's kind of a shame, right? Because you would want to think that the granularity with which you describe events somehow shouldn't matter. Maybe that's naive to think that it couldn't.
Yeah,
maybe it must matter. But.
Right. So remember that it goes back to our NUPS question that we're doing something for categorical data. Everything is distinct. So it's not like you've seen like you quantize into level 2 to distance 1 and then quantize to distance half. Every element is on its own. So yeah, I agree with you, it would be nice, but it's because we don't have this notion of things are close and things are more granular. Then if you combine, you're just combining 2 different elements.
Could you at least maybe say that if I give you the finer grained data, you'll have less attenuation?
So if you applied the whole technique from the beginning, so it's a different question, right? I mean, you applied the whole technique from the beginning to the lower resolution data?
Yes.
Yeah, I suspect so. I cannot see it.
To the higher resolution data, more fine grained data.
No, the larger the alphabet size,
yes,
the higher the attenuation you will have, but it will saturate at square root of n, right? Or 2 to the square root of n, depending on, it will saturate at square root of n. The largest the alphabet size, we expect the attenuation, which is the log, just the log of the, we expect the attenuation, the redundancy is the log of that, to go up. But the attenuation will saturate at 2 to the square root of n, regardless of the alphabet size.
I see. Okay. But that's interesting. So the fact that I've given you more information actually hurts you.
But that's to be expected because you're trying to estimate distribution of a larger alphabet. And mind you, we're looking at the worst case.
Oh, no. But then you coarsen it again at the end.
Oh, okay. So
you take in both cases, you...
From both, maybe I answered the different question from what you asked. Yeah. I'm answering the question of what happens if you look at the fine data from beginning to end versus you're looking at the coarser data from beginning to end. Maybe that's not what you...
It's not quite the question.
Okay,
no.
yeah.
We can take it offline.
Okay.
Other people
but for that question, that is the answer.
For that question, I believe your answer.
I think the second question will be harder to answer because the attenuation is defined as P of x over Q of x, right? So it's almost, once you change your definition of what x is, it's almost like P of x1 plus x2 divided by
exactly.
Q of x1 plus Q of x2. So there are some...
Exactly.
But it's not obvious to me. Well,
So you're hoping that, so you're trying to compare a hybrid method to something?
No, I mean, it's the same commutation diagram that I was describing a minute ago, where what I have in mind is a fine-grained distribution. I'm generating the data from a fine-grained distribution, but I'm only asking you to generate a particular coarsening of that distribution.
I see, yeah.
And I could either show you the original fine-grained data that I generate, and you could run your method on that, and then coarsen the result, or I could coarsen the data before I give it to you. And I would hope that even if you don't get the same answer, that if I gave you the fine-grained data to begin with, that your estimation of my true distribution would be, the coarsening of my true distribution would be more accurate.
Yeah, I'm not sure. I mean,
These are
it
just
makes
kind of
sense.
sanity
Yeah,
checks, right? So you were doing some sanity checks with your quiz. Like, does this do the right thing in the case where you have DNA and everything is new, and
Right.
you predict that new things are coming?
Right. So the sanity check here, one of them is to say that if you give me the coarsening of the data from the beginning, then it will do better, I'm pretty sure. Right. But you're asking about a comparison which I'm not 100% sure I understand. But, okay. Yeah.
Okay, thank you very much.